All right, so in this video, we're going to review intermolecular forces, and then we're also going to talk about Coulomb's law. All right, so remember we have intermolecular forces and intramolecular forces. The intramolecular forces are going to be the forces that's within molecules and ionic crystals. Those will influence things such as shape, bond energy, and then somewhat chemical behavior. So intramolecular forces are going to be stronger than intermolecular forces. And examples of intramolecular forces would be ionic bonds and covalent bonds. So intermolecular forces will strongly influence physical properties of molecular liquids, solids, and gases, and they are weaker than intramolecular forces. So for intermolecular forces, we're going to look at molecules, which if you recall are covalent compounds. So here's a picture showing the difference between intramolecular forces and intermolecular forces. Again, intra, Ra, is the actual chemical bonds, but inter is going to hold one molecule near another molecule. That's what's going to be responsible for substances being in a solid or liquid phase. Here's another picture showing the difference between them. So for instance, this hydrogen to oxygen bond here is a polar covalent bond. So that's an intramolecular force. And then here, this is an intermolecular force, what's holding one water molecule near another water molecule. And recall that I said intramolecular forces are stronger than intermolecular forces. So for example, if we were looking at water molecules and we were looking at separating ice, so different H2O molecules to form a liquid phase, that's going to look at overcoming the intermolecular forces, right? Separating molecule from molecule would be an molecular force. Whereas if we're trying to actually break this bond here from hydrogen to oxygen, that's looking at an intramolecular force, okay? So intermolecular forces are weaker than intramolecular forces. They also, intermolecular forces, again, is going to explain different states of matter. So solids are going to have strong intermolecular forces, which allow the particles to be close to one another and tightly compact. Liquids have weaker intermolecular forces than solids. What's happened when we go from a solid to liquid is we put in some energy to somewhat separate or break those intermolecular forces, but the particles can't completely overcome those intermolecular forces. So they do have more room to move, but they're still kind of going to flow over one another. They can't completely separate. Whereas if we're looking at a gas, we assume that they have no intermolecular forces, so they're free to move around however they please. They're free to move around randomly. So again, remember one of the parts of kinetic molecular theory said that gas molecules did not have any intermolecular forces, that they didn't have any attractive forces to another gas molecule. All right. So intermolecular forces will explain other physical properties such as boiling points or melting points. The stronger the intermolecular force, the higher the boiling point, right? So if some substance has strong intermolecular forces, you have to put a lot more energy into separating those molecules. So that means the boiling point is going to be higher. So 4 types of intermolecular forces we'll cover in this video are ion-dipole interactions, dipole-dipole interactions, and these first 2 are going to be really similar. It's just whether we're looking at an ion with a polar molecule or whether we're looking at polar molecules and other polar molecules. And then we also have London dispersion forces and hydrogen bonding. Now you might also see this term called van der Waals forces. Van der Waals forces are the weaker intermolecular forces, so it kind of groups dipole-dipole and London dispersion forces together. All right, let's jump to, before we can talk about a ion-dipole interaction or a dipole-dipole interaction, we have to first discuss what a dipole is. So dipole, or sometimes you might see this referred to as a dipole moment, is going to be a molecule that has a center of a partial positive charge and a center of a partial negative charge. Essentially, to identify if something has dipole-dipole forces, that means it's going to be a polar molecule, right? Polar molecules will have dipole-dipole interactions. Nonpolar molecules will not. Now, when you're looking at these diagrams showing dipole moments, you'll have these arrows with like a little cross at one end. The arrow is going to point in the direction of the net negative charge. So it's pointing in the directions that the electrons are being pulled towards, right? And here in this example, this is a water molecule, of course, and hydrogens, both of the hydrogens, are going to have this partial positive charge, which is represented with this sigma here, and the oxygen would have a partial negative charge. And the reason that oxygen has a partial negative charge is it is more electronegative than hydrogen, so it's pulling those electrons closer to it. These electrons are not being shared equally between the oxygen and hydrogen atoms, so the electrons in this bond are pulled a little closer to oxygen and a little further from hydrogen. So that causes oxygen to have a partial negative and hydrogen to have a partial positive. Now, you can tell if a molecule is polar based on the positions of the atoms on the periodic table. So first, to determine if a molecule is polar, let me back up. To determine if a molecule is polar, you got to identify two things. One, you got to look to see if you have polar bonds, and then two, you got to check for symmetry. So first, we're going to describe how to identify if the bond itself is polar or nonpolar. So polar bonds are going to occur when you have differences in electronegativity values. Essentially, what this means is if we have atoms of different elements bonded together, they're going to generally be considered polar. There is an exception. Carbon-hydrogen bonds, we usually consider those to be nonpolar because the electronegativity values of hydrogen and carbon aren't too far apart. Okay, so a carbon-hydrogen bond is usually, we consider it to be nonpolar. So if it's not a carbon-hydrogen bond or if it's not a diatomic, it's probably a polar bond. Okay, so some examples. Carbon-chlorine. That is not a diatomic. It's different elements that are bonded together. So they're going to have different electronegativity values, so that's going to be a polar bond. HF would also be polar because it's different elements that have different electronegativities. Carbon-carbon, on the other hand, would be nonpolar because each of those carbon atoms have the same electronegativity value. Same thing with oxygen-oxygen, that's nonpolar. Carbon-hydrogen is nonpolar because, like I said on the previous slide, we consider CH bonds to be nonpolar. And then SF is going to be polar. All right, so here's a picture of a diatomic, and it's showing that there's no net dipole moment. This is a nonpolar molecule because those electrons are going to be shared equally because this chlorine has the same electronegativity value as the right chlorine. So there's an equal sharing there. Now, just because the bonds are polar doesn't mean the entire molecule itself is polar. To check if the molecule is polar or nonpolar, we're going to have to look out for symmetry. So if the molecule has polar bonds and symmetry, then those poles are going to cancel one another out, and that would give a nonpolar molecule. There would be no net dipole moment. So one example we'll look at here is carbon dioxide. We see the left oxygen to carbon is a polar bond, because it's different atoms. They have different electronegativities. Oxygen, of course, is more electronegative than carbon. And then same thing on the right side. This carbon to this oxygen bond is also polar. But we have a polar bond to the left and the same exact polar bond to the right. So those poles are going to cancel one another out. You can kind of think of it as like a tug of war. There's the same strength pulling to the left as there is to the right. So it's canceling one another out. So overall, CO2 is going to be a nonpolar molecule. Now, the atoms don't have to be linear to be, or sorry, the molecules don't have to be linear to be nonpolar. For instance, we could have trigonal planar molecules, and as long as it's the same atoms bonded on the outside, the same outer atoms, then those poles will cancel one another out, and so it would give a nonpolar molecule. Okay. Now, on the other hand, we looked at in the previous slide, this was for trigonal planar, but if you're looking at trigonal pyramidal, and those can occur when you have an electron pair on that central atom, so a lone pair on the central atom, those will have a net dipole moment. Because of that extra electron pair, electron pairs will throw off symmetry and will cause a net dipole moment. Okay, now an important note too is those bonds have to be identical for it to be symmetric. So here, the left molecule, carbon tetrachloride, is going to be nonpolar because it's the same type of bond all the way around it, a carbon to chlorine. But if we were to replace one of those chlorine atoms with a hydrogen, now these bonds are not identical, so this molecule is polar. Okay. And then there's still a whole bunch more examples here. Again, if you add in lone pairs will cause molecules to have a bent shape, as we talked about in the Vesper theory video. So that will throw off the symmetry and cause the molecule to be polar. This is why water, H2O, which would have a very similar Lewis structure to H2S because oxygen and sulfur are in the same family. So this is what causes oxygen to be, or sorry, water to be polar. Because of those lone pairs, it's bending the molecule and throwing off the symmetry. So now there is going to be a net dipole moment. All right, so now that we've discussed dipole moments, we can now move into identifying ion dipole interactions and dipole-dipole interactions. So ion dipole interactions are going to occur when there is an ion and a polar molecule. So it's an interaction between that ion and the partial charge on a polar molecule. So for instance, if we're looking at, say we're looking at a cation, something that has a actual full charge here, not just a partial charge. So let's say we're looking at the cation Na+, sodium. And let's say the polar molecule we're looking at is HF. HF we know is polar because this H to F is a polar bond and there's not any symmetry here, so this is a polar molecule. And in this polar molecule, the hydrogen would have a partial positive charge and the fluorine would have a partial negative charge because fluorine, sorry, is more electronegative than hydrogen. So if we have a bunch of HF molecules surrounding a sodium plus ion, the HF molecules are going to orient themselves so that way the negative area, which in this case is the fluorine side, is going to be closer to the positive ion. So the fluorine ions would be all of these little red ones here, or sorry, not the fluorine ions, the fluorine atoms would be these red areas here, and they would orient themselves so that way they are close to that positive cation, right? Because opposite charges attract. Whereas if we looked at the other side over here, so say we're looking at Cl minus, is now an ion we have in there. Cl minus and HF would have ion dipole interactions, and in these cases, the H atoms in HF would orient themselves closer to the negative anion, so that's Cl minus ion. Okay, so some things that will increase the strength of those interactions are the charge on the ion and the magnitude of the dipole moment. And what that means is the larger the difference in electronegativity values. So as a shortcut for that, you could think the further the atoms are spaced apart on the periodic table, the greater their difference in electronegativity values. So the greater this dipole moment would be, right? The stronger the dipole moment. So the strength of those interactions is going to increase as the charge on the ion increases. So say if we're looking at that previous example, Mg2+ would have stronger interactions with HF than Na+. Okay. All right. So that was ion dipole interactions. The next one we're going to look at is dipole-dipole interactions. And these are really similar to the ion dipole interactions. But instead of there being an ion and a polar molecule, dipole-dipole is going to look at two polar molecules interacting with one another. And in these cases, the opposite ends of those partial charges are going to be attracted to one another. So like if we're looking at HCl and HCl, the chlorine part of one of the molecules would be attracted to the hydrogen part of the other one. Now, a lot of times these are only going to be effective when those molecules are close to each other, right? Because if they're too far apart, there's not really going to be any kind of interaction. And these intermolecular forces are going to be weaker than their ion dipole forces. But just like with ion dipole, the strength is going to increase with an increase in the magnitude of the dipole moment, or in other words, it's going to increase with an increase in polarity. So the more polar the molecule, the greater that difference in electronegativity values, the stronger these interactions. All right. So ion dipole interactions can affect the boiling point, just like all of the intermolecular forces can. And your boiling point is going to, or the substance's boiling point is going to increase as the dipole moment increases. So again, as the polarity increases, the intermolecular forces are going to increase, or specifically the dipole interactions will increase. And that means that the boiling point is also going to increase. So if we're looking at something like propane, which has just a bunch of carbon-hydrogen bonds or carbon-carbon bonds, it has a very low dipole moment, right? Because we said that carbon-hydrogen bonds are considered to be nonpolar. Whereas if we were to jump with something that has nitrogen in it, now we have a larger dipole moment, so a greater polarity in this molecule, and that's going to cause the boiling point to be greater as well. All right, so that was the first two types, which were ion dipole and dipole-dipole. The next type we're going to look at is London dispersion forces. So ion dipole and dipole-dipole, molecule that was polar. However, if only polar molecules had intermolecular forces, then we wouldn't be able to explain why nonpolar gases would be able to liquefy, right? Why could they turn into a liquid which has intermolecular forces if nonpolar things don't have intermolecular forces? And that's because there are intermolecular forces, but instead of, it's just a different type. These types are going to be called London dispersion forces. So the idea of a London dispersion force is that these temporary, or it could also be called instantaneous or induced, dipole moments are going to form. So let's say, for instance, we're looking at helium. It's just an atom, so it's not polar. So we don't have dipole-dipole interactions, but why could we cause some of those gases, those nonpolar gases, to convert or condense into a liquid? And that's because we have these temporary dipoles that can form. So in this helium example, a helium atom would have 2 electrons. And let's suppose, since those electrons can move, that they happen to move to the same side at some instant. In that instant, there's going to be a partial negative charge over here where the electrons are. And now, since there's no electrons on the right side, that's going to form a partial positive area. So it creates an instantaneous dipole. Okay. All right, so your London dispersion forces, again, are attractions between these instantaneous dipoles and then what they'll call an induced dipole, because one of them can form an instantaneous dipole with the electrons moving or gathering on one side, and that can cause a dipole to form in another nearby atom. Now, your London dispersion forces generally are considered to be the weakest of the intermolecular forces, but an important note, if they are giving you the boiling points of the substance, that automatically tells you who has the strongest intermolecular forces. So it could be that, say, substance A has a boiling point of, let's say, I don't know, 15 or 50 degrees Celsius, and substance B has a boiling point of 80 degrees Celsius. From that information alone, we automatically know that B has to have stronger intermolecular forces. It doesn't matter if A had dipole-dipole and London dispersion and B just had London dispersion. It just so happens, because we're given the boiling points, that the forces in B have to be stronger than the forces in A. All right, so London dispersion forces are going to be present in all of our molecules, okay, polar and nonpolar ones, but usually they're only significant when no stronger force exists. Okay. All right, some things that affect London dispersion forces. This is a really important term here, and that's called polarizability. Okay, what this means, kind of in a nutshell, is the ability of that substance or molecule to form poles, right? So polarizability is going to increase with molecule size, and the primary reason it does that, so I wouldn't say it increases with molecule size just because of molar mass, or that, like I said, with mass, I wouldn't say that. I would focus more on the electron aspect. So the larger our molecule, the more electrons it has, and so the more electrons it has means that there's more electrons that are free to move and form poles. Okay, so that's our first reason, and then here is our second reason. So, all right, so second reason for polarizability increasing with molecular or molecule size is that larger molecules, so as in molecules with larger atomic radii, indicates that the electrons are further from the nucleus, and there's a smaller attraction between the nucleus and those electrons out there. So they're likely more free to move around and form those poles. All right, so here's some examples showing how the size of the molecule increases with the boiling point. So that also tells us that increasing the size of the molecule increases the intermolecular forces. But again, I wouldn't focus on it from the molecular weight. I would focus it more on the electrons, because it's the electrons themselves that's explaining these intermolecular forces, not the molar mass. All right, so iodine, or I2, diatomic iodine, is going to have a whole lot more electrons than these other diatomic halogens. So more electrons and a larger size for the atom in terms of the radius means that there's more room to make poles, or a greater chance to make poles. So the polarizability of I2 is greater than the polarizability of Br2 or Cl2 or F2. So I2 is more polarizable, and because of that, it has stronger intermolecular forces and therefore a greater boiling point. All right. Another thing too that can affect the strength of the London dispersion forces is the shape of the molecule. If molecules are shaped in a longer chain, so like N-pentane here, there's a greater or more spots to form these poles. So it is more polarizable and has stronger dispersion forces than, say, neopentane. So N-pentane and neopentane are going to have the same structural formula, as in they'll have the same number of atoms of each type of elements here, like the same number of carbons and the same number of hydrogens. But what will be different is N-pentane, since it's a longer chain, whereas neopentane's like a clustered ball, N-pentane has more room to form, or more areas to form these poles, those dipoles. So because of that, N-pentane would have stronger London dispersion forces than neopentane. All right, so our last type of intermolecular force is hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole interactions, dipole-dipole forces, but specifically it is or occurs in polar bonds with hydrogen and either fluorine, oxygen, or nitrogen. So it's a super large difference in electronegativities. Okay, so it's a very polar bond, essentially. So it occurs again when hydrogen is bonded to either fluorine, oxygen, or nitrogen, and the actual interaction is between that hydrogen and the fluorine, oxygen, or nitrogen atom of another molecule. These are going to be considered the strongest of our intermolecular forces. But like I mentioned again, or previously, and I'll mention it again, if you're given boiling point, that automatically tells you, regardless of what type of intermolecular forces the substances have, the boiling point automatically tells you who has the stronger intermolecular forces. All right, so here, this red with the little dotted lines represents the hydrogen bond, or that intermolecular force between these molecules. So again, if we look at this right water molecule, we have this hydrogen is bonded to oxygen, and the interaction is between that hydrogen and another molecule's oxygen. Okay, so it's not this actual bond here between this hydrogen and the oxygen it's actually bonded to. The hydrogen bond is an intermolecular force between that hydrogen of one molecule and then the electronegative atom of the other. All right. So let me jump ahead here. Here's a little flow chart too on identifying or IDing the intermolecular forces in various molecules. So first, you want to ask yourself if there's polar molecules. So if there's not polar molecules, then there's just London dispersion forces. If there are polar molecules, you would want to ask, are the hydrogen atoms bonded to nitrogen, oxygen, or fluorine? If the answer is yes, then you have not only London dispersion forces, because all of the molecules have that, but you also have dipole-dipole forces, and more specifically, hydrogen bonding, because remember, hydrogen bonding is a special case of dipole-dipole forces. And then if there's polar molecules and ions, then you'll have ion-dipole forces. Okay. All right, so intermolecular forces is what we use to explain attractions between different molecules, which, if you'll recall, are covalent compounds. On the other hand, Coulomb's law we can use to explain interactions between ions in an ionic compound, or we can also use it too for the concept of ionization energy. So here's the same slide that you saw in a previous video, but again, Coulomb's law, relates the either attractive or repelling force between two charged particles, and the size of those particles, the size of the, or why am I saying particles? The size of those charges, Q1 and Q2, is directly proportional to that force, and that force is inversely proportional to the square of the distance between them. Okay, so if we take this and compare it, there's two situations where we would likely apply Coulomb's law. The first is if we're looking at individual particles, so either atoms or ions, and explaining or using Coulomb's law to explain ionization energy. So this is a huge block of text, but explaining this, so I'm going to shorten it. All right, let's suppose we are looking at ionization energy. And suppose we're looking at the ionization energy that's comparing two elements in the same period. So in a previous video, we looked at lithium and beryllium. Lithium, we can say is, let's say for ionization energy, the two charged particles that we're looking at and their attraction to one another is the nucleus. So Q1 is going to be the nucleus. And Q2 will let be the electron, right? Because ionization energy is how much energy it takes to remove a valence electron. So we'll let that be -1. That's a valence electron. So if we look first at lithium, lithium's nucleus has 3 protons in there, okay? Whereas beryllium has 4 protons. Both of them, if we're looking at the energy to remove one of their valence electrons, that valence electron has a charge of -1. Lithium and beryllium, comparing them using Coulomb's law, Q2 over R squared. All right, so for lithium, our Q1 would be +3 and Q2 would be -1. That's going to give us a larger value, or sorry, a smaller value up top than if we were looking at beryllium. So that means the attractive force from lithium's nucleus to its valence electron is less than the attractive force from beryllium's nucleus to its valence electron. So that means that beryllium, with the greater attractive force, would have the larger ionization energy. Okay, so we can use Coulomb's law to explain why ionization energy increases going to the right. We can also use it for explaining ionization energy of elements in the same group. So if we're looking at group trends. All right, so suppose we're looking at sodium and let's say potassium. Sodium has in its nucleus 11 protons, and potassium has in its nucleus 19 protons. And sodium has 1, 2, 3 energy levels, 2, 8, 1. And potassium has 4 energy levels, 2, 8, 8, 1. So in this case, the radial distance, the R distance between the nucleus and that valence electron is different for these two atoms. So if we're to write Coulomb's law again, Q1, Q2 over R squared. So although these values are going to be different, sodium would be 11 plus and potassium would be 19 plus. So although potassium has a greater charge in its nucleus, this R term is squared. So this R term is going to be the dominating factor here. That's explaining the difference in the ionization energies between potassium and sodium. So since potassium has a greater distance from nucleus to valence electron than sodium does, then increasing this denominator term decreases that attractive force. So it tells us that potassium's nucleus, its attraction to its valence electron, is less than the attraction from sodium's nucleus to its valence electron. So a smaller attraction means that it's easier to take away one of those electrons. So there's less energy required to remove the valence electron in potassium, which explains why its ionization energy is smaller. So that's the first thing we can use Coulomb's law for. And the second one is lattice energy. So lattice energy is how much energy is needed to separate oppositely charged ions, so to separate cations from anions. The greater this lattice energy, the stronger the ionic bond. Okay. So in these cases, instead of it being the attraction between a nucleus and a valence electron, we're looking at the attraction between a positive ion and a negative ion. So if we look at, let me rewrite Coulomb's law again, Q1, Q2 over R squared. Let's say we're comparing sodium chloride to magnesium chloride. Which one of these would you expect to have the greater lattice energy? You can use Coulomb's law to predict this or explain this. So if we were to separate these, sodium would have a +1, chlorine would have a -1, magnesium would have a 2+, and chlorine would have a negative still. So here in this case, the charges are different. And is the size of a sodium substantially different than the size of a magnesium ion? No, right? Because they're in the same period. Sodium's right beside magnesium. So although sodium is going, or Na plus is going to be larger than Mg2 plus, their sizes are pretty similar to each other. So instead, what we're going to look at in this case is the charge, okay, of each of those. So sodium would be a +1 attracted to a -1, whereas magnesium would be a +2 attracted to a -1. So the attractive forces in magnesium chloride is going to be greater. So this means that magnesium chloride would have a greater lattice energy than sodium chloride. All right, so we can also do that with other examples, because that was an example where the cations were in the same period. So let's suppose we're looking at an example where the cations are in different periods, but in the same group. Okay, so in these cases, we're going to change the size of them, but not change the charge on the ions. So say we're looking at sodium chloride versus potassium chloride. Sodium chloride, if we split it again, sodium would be a +1 and chlorine would be a -1. Potassium chloride, if we split it, we'd have +1 and -1. Okay. So in these cases, there's no difference in their numerator for this calculation, right? So Q1 for sodium chloride would be +1, and then Q2 would be -1. Same thing for potassium chloride. So the size on the charges are the same. But what is different between them is the size of these cations. So sodium would have 1, 2, 3 principal energy levels, whereas potassium would have 1, 2, 3, 4 principal energy levels. So what that means is this potassium ion is further from the chloride than the sodium ion is from chloride, right? Because these two chloride ions are going to be the same size, but what's different is the size of these cations. So since potassium's larger, there is a larger distance between potassium and chloride than sodium and chloride. So since this distance is going to be greater for KCl, this denominator term is greater, which causes this whole fraction to decrease. So the attractive force between potassium ion and chloride is less than that for sodium ion and chloride. So that means that sodium chloride in this case would have the greater lattice energy than potassium chloride. All right. So that is all for this video.